As our understanding of atomic physics grew, we came across a couple of interesting things. One is this. If I have a light source, broad spectrum one, like maybe the sun, and I shine it through, I'm going to give this a box with hydrogen gas in it. I see a spectrum out the other side. Now, if I look from this side where there's nothing in the way, I will see a spectrum that looks like this. I'll see a spectrum that looks like this. But if I first let that sunlight pass through a sample of hydrogen gas, I end up seeing a spectrum that looks a little bit different. I see something a little bit more like this. I've got a line missing here, and I've got a line missing here, and there's one missing here, and there's one missing here. This thing would be a full spectrum. This is a full spectrum, but there are lines that are missing. So there are these spaces that we have to account for, and we do account for them. We might have separately a spectrum we draw that looks like this, that has only those lines. This top one is called absorption spectrum, and this bottom one is called an emission spectrum. And as you can see, they just add up to be a full one, a full spectrum. So what's going on is this sunlight is coming in, it's hitting this hydrogen, and some of these rays are being absorbed by the hydrogen, and some just pass through. The ones that are being absorbed, those come out in this emission spectrum. So there are wavelengths here that are missing. I'm going to put that in quotes. There are wavelengths that are missing. They're missing from the full spectrum view. And the Bohr model is an effort to explain where these are coming from. Somehow or other, these must be wavelengths of light that hydrogen is using. It can't use, these wavelengths here in the middle, but if we give it this wavelength of light, then it can use that. And that's what we're talking about. That's the question that we are trying to answer with the Bohr model. The Bohr model says this. It says, the Bohr model works with a hydrogen atom, and the reason it works with a hydrogen atom is because hydrogen is so simple. Hydrogen has a single proton, and then around that it has an electron somewhere. So what the Bohr model does is it states that that electron can live in one orbit or in another orbit, but not between them. It does treat these electrons as living in orbits, which we have come to find out is not actually entirely accurate, but the numbers work really well. This is a pretty good model. What it says, if I've got this electron and it's living in this orbit, it can be promoted up to this orbit. And in order to do that, it needs to gain some energy. That energy has to come from somewhere. So if we have a light ray coming in, especially when we have like broad spectrum light, we are saying we have pretty much every color coming in, right? And we have infrared, and we have ultraviolet, and all those also. I mean, we are not limited to just what we can see, but we have every band of light coming in, is the point. When all those bands of light come in, there is some frequency of light, some wavelength of light, that this electron says, that's the one I need. So it says, if I can absorb this, let's say this photon right here, if I can absorb this bit of light right here, that's going to be enough to allow me to, so I'm going to take this one, absorb this, and when I do, that's going to be enough to allow me to jump to this level. Now, from the other side, I have this remaining spectrum that comes out. So I had this coming in, full spectrum light coming in. The electron said, give me that blue, I can use that. It absorbed that, and so I'm left with not all of the light coming in anymore. And that made this make sense. What this means then is for this hydrogen atom, I have different energy levels, and that might look like this. I have my proton in the middle, and I have these different energy levels. N equals 1, N equals 2, N equals 3, N equals 4, N equals 5, and so on. Each one has its own energy, each one has its own angular momentum, which is how we actually develop this model. But the point of the Bohr model is we can live in one of these electron levels or another. We can move from one to the other, but we can't just hang out in the in-between space. That's not allowed. We end up with a mathematical formula that looks like this. This is called the Rydberg formula, and R is the Rydberg constant. And it is 1.097 times 10 to the 7th inverse meters. This is kind of a wild formula. It gives you the wavelength of, this is the wavelength of the photon needed. And these ends are the initial and starting, or the initial and final energy levels for that electron. So if I've got an electron that's sitting here in the n equals 2 level, and I would like this to jump up to the n equals 5 level, a 2 to 5 transition, I'm going to say 1 over the wavelength equals R times 1 over 5 squared minus 1 over 2 squared. And I can plug those numbers in, and I get 4.34 times 10 to the negative 7th meters, or if you like, 434 nanometers, which lands me right inside the visible spectrum and gives me blue light. So I am, in jumping from the n equals 2 to the n equals 5 level, I have to absorb some light. When I talk about absorbing light, I'm trying to treat light as a particle, so I'm going to absorb a particle of light, which we call a photon. A photon has a frequency and a wavelength and an energy. I would like to absorb a photon with a wavelength of 434 nanometers. When I do that, I get exactly the right amount of energy to jump from 2 to 5. This also means that I've got some kind of a formula for the energy levels of this atom. And I do. These energy levels are going to stack up. So first, we're going to have our n equals 1 energy level. Then we'll have an n equals 2. Then an n equals 3. I'm drawing these intentionally closer together. Then 4. And these will keep stacking up and getting closer and closer together. So my electron, which I generally draw as an arrow, can jump from one level to another level if the energy that it picks up from a photon is equal to whatever that height difference is, whatever that energy difference is. So what I've got when I write this is I am making a list of electronic energies so that I can jump from one to the next. I can come up with a list of values. I'm going to do that in a separate video so that this one doesn't get too terribly long. I can come up with a list of values. I'm going to need to talk about some different energy units. But for right now, this is the idea of the Bohr model.